Welcome back. In this video, we're going to talk about an application of the definite integral that allows us to find the area bounded between two curves. So let's jump right in. Let's suppose that we're given two distinct curves, say f of x, y equal to f of x, and g of x. And we would like to know the area bounded between these two curves, between two values, a and b. So that will be this pink shaded region right in here. And so what we can see is that if we were to calculate the definite integral of f of x from a to b, we would get all of the pink shaded region, and then we would also get all of this black shaded region as well. But if we calculate the definite integral of g of x from a to b, we would just get the black shaded region. So that means that if we subtract the definite integral from, of f of x from the definite integral of g of x, all between a and b, we will be left with exactly that pink region. So we can write this explicitly. We can say that if f of x is bigger than or equal to g of x, and f and g are continuous, on AB, both of these hold true on the entire interval, then let's emphasize this, the area between f and g on AB is given by the area is equal to this definite integral of f of x minus g of x, all integrated over a to b. Now, the first thing that I want you to notice is because f is larger than or equal to g on the entire interval, by definition, by property 7 of definite integrals, this is non-negative. So it's a proper area that we're talking about here, right? That's an important distinction. Second of all, we can use the additive property of definite integrals to break this up to see exactly what I was saying to start. This is the same as the area bounded below f of x subtracting off the area bounded below g of x, right? So I'm just rewriting it to make it more compact above, but you can easily distribute it to get back to what I was talking about right here. Okay, so the principle is fairly simple. So let's see it in action. Let's do some examples here. So let's say, as an example, let's find the area bounded, so BNDD, that's my short form for bounded, above y is equal to 2 e to the minus x plus x, and below y is equal to e to the x over 2 on the left by x equal to 0, and on the right by x equal to 1. Okay, so let's give it a little sketch, just so we can visualize a little bit what exactly it is that we are drawing here. And so our function, I believe actually this should be below. Okay, so let's jump right in with an example here. Let's say find the area that is bounded below y is equal to 2e to the minus x plus x, and above y is equal to e to the x over 2 on 0 to 1. So let's offer up a quick sketch so that we can visualize this area that we're working with. In this case, the upper function is 2e to the minus x plus x. So that is at 2 when x is equal to 0, roughly coming down like this. Let's use a green curve for the lower piece. This is e to the x over 2. So in this case, we might get something that looks roughly like this. Sorry, that's 1/2 there. So this is e to the x over 2. The red curve is given by 2e to the minus x plus x. And our integration bound here is given from 0 all the way up to 1. So this is the region that we are interested in, right in here. We can see the red curve. We are told the order of these curves, so we can calculate this area. So our area is the integral from 0 to 1 of the upper curve. That's 2e to the minus x plus x, minus the lower curve, e to the x over 2 dx. And in this case, these are fairly straightforward functions to find the antiderivatives of, because exponentials just differentiate into exponentials. Polynomials, we just need to raise the exponent, divide by the new exponent. So let's go ahead and find the antiderivative here. We get minus 2e to the minus x plus x squared over 2 minus e to the x over 2. And in this case, we are running from 0 to 1. So at the upper bound, maybe I'll put this in brackets, 2 to the minus 2 times e to the minus 1 plus 1 squared over 2 minus e to the 1 over 2. And subtracting from the lower bound is going to be minus 2 e to the 0 plus 0 squared over 2 minus e to the 0 over 2. And, after a little bit of algebraic manipulation here, you just sort of need to clean this up. You can find that this is equal to 3 minus 2e to the minus 1 minus e over 2, which, if you want to put this into a calculator, this is approximately equal to 0.9051. The actual value is not really that interesting to me. What's interesting to me is how we got there, right? And it was just through a definite integral. Okay, let's take a look at another example. So this is example number 3 today. And this asks us to find the area of the region in the first quadrant that is bounded above by y is equal to the square root of x and below by the x-axis and the line y is equal to x minus 2. Okay, so this one is slightly more complicated. Let's give it a little sketch to see what we're working with. Let's start with the square root of x function. So here we have y is equal to the square root of x. Now, if we take a look at what this is telling us, it says it's bounded below by the x-axis and the line y is equal to x minus 2. Now, the line y equal to x minus 2 has a root at 2, and it's negative beyond that. Now, we're looking just in the first quadrant, so it tells us that the lower bound is made up of the x-axis in this case, so the curve y equal to 0. And then beyond that, the lower bound of this region is made up of the curve y is equal to x minus 2. So what we can see is that there are two different lower bounds, and that means that our analysis here is going to have to be broken up into two different components. So we say that there is area 1 here and area 2 here, and the total area is given by area 1 plus area 2. So what we can see is that to build area 1, we need to find the region below the curve y equal to the square root of x, because the lower bound is just the x-axis. This is the usual definition of a definite integral. So that means that the area is equal to the integral from 0 all the way up to 2 of the square root of x. Square root of x minus 0 technically, but we're not going to put the minus 0 in there because it's just not necessary. And then plus, so just for our own notes, this is area 1. And plus the definite integral from 2, and we'll determine where this integrates up to, of the square root of x minus x minus 2, upper bound minus lower bound. And again, this is equal to area 2 in this case. So the question is, what is the upper bound? Well, the upper bound is given by this point of intersection, so much like the previous example. So the question is, what is that point of intersection? Well, this is when the curve square root of x is equal to x minus 2. Now, in order to solve this equation, we're going to square both sides. This gives me x is equal to x minus 2 squared, which gives me x is equal to x squared minus 4x minus 4, which I can rearrange into solving for the roots of a quadratic polynomial. I can factor this thing. And then this gives me the solutions at 1 and 4. Now, there are two solutions, but there is only one point of intersection. So that's the first thing that we should address. So where did the second solution come from? Well, the second solution came from the fact that we're solving a quadratic equation. This comes from the fact that we squared this equation. Now, the x equal to 1 is certainly not present as a point of intersection on our graph, right? From the picture just to the left here, we can see that it's clearly not going to be x equal to 1. This is just an artifact from that squaring that we did at the beginning. So we can rule that one out. And it tells us that our point of intersection is at x equal to 4. This point is given by 4, 2. So this means that the upper bound on the integration here is given by 4. So now we're left with a relatively straightforward integration here, because everything in here is just x to the power of some exponent, n. So let's go ahead and do this. This becomes 2/3 x to the 3 over 2, running from 0 to 2, plus 2/3 x to the 3 over 2 minus x squared over 2 plus 2x. Remember that minus here gets distributed into both terms, the x and the minus 2. And this is running from 2 to 4. Now, I'm going to leave you to do the algebra on your own here. You're essentially just plugging in the upper bound and subtracting it from the lower bound in each term. But in this case, you get a total area of 10 over 3. So you have an answer. If you're following along, try and do this on your own and make sure that you get exactly that answer. There's another way that we can approach the previous problem that doesn't require us to break up the regions that we're integrating over and have us doing two separate definite integrals. And we're going to approach this by integrating in terms of the variable y instead of the variable x. So let's start by sketching out the regions first, and I'll show you what I mean here. So let's start with the square root function. And the lower bounds on this region were given by the x-axis, and the curve y is equal to x minus 2. So what we can alternatively do is we can ask ourselves, what is the region bounded between these curves and the y-axis instead? So we're still looking for the same region in here. But what we can do is we can think of this horizontally instead of vertically, where we can think of the region bounded from the green curve over to the y-axis, subtracted from the region bounded from the red curve over to the y-axis. The same principle of using Riemann sums to build up integrals in this way works exactly the same. You just have these these horizontal rectangles that are used to build up to the definite integral, but it's exactly the same principle. So really the first step to applying this thing is rewriting the functions that were given as functions of x as functions of y. We're gonna let y be our independent variable. So y is equal to the square root of x is the same as saying x is equal to y squared, just square both sides. Similarly, y is equal to x minus 2 is the same as saying x is equal to y plus 2. So now what I have is that if I give you a value of y, I can tell you the corresponding value of x along that curve. And so that means that now to find this area, we just need to integrate from y equal to 0 right here. And we already calculated this point to be 2, 4. So up to 4 right here of the area bounded from the y-axis to the upper curve, or the rightmost curve in this case, the green curve, minus the area bounded between the y-axis and the lower curve, the leftmost curve, and that's the red curve. So in this case, what we get is a much simpler equation for calculating this thing. The area becomes the definite integral from 0 to 4 of the upper curve, that was y plus 2, minus the lower curve, which is y squared. And now we're integrating with respect to y. Nothing changes, right? Remember, I've emphasized this a few times. The variable doesn't matter. You can call it theta, you can call it x, you can call it y, whatever you want to do. It just matters that we are integrating the terms, these y terms, with respect to y. That's the thing that matters here. So in this case, again, these are fairly easy functions to find antiderivatives of. We get 2y plus y squared over 2 minus y cubed over 3. I did some rearranging here just so that we have ascending degrees in y. And again, I'm going to spare you the details right now. This is essentially a calculator problem, but we get exactly the same area that we got before. But look at how little work this actually took me, right? This was almost as simple as the first example that we did in this lecture. So we have ways of viewing these things. One way might be slightly harder than the other, but we have this new method that's now accessible to us where we can integrate in terms of y as long as we can pose the functions with their independent variables in y.